Yeah, hello everybody. I would like to welcome you to our webinar about calibration of wavelengths dispersive X-ray fluorescence instruments. I would like to guide you a little bit through the way how to do this kind of calibration, how to set up a calibration from scratch. And I also would like to present you a way as a new kind of online course you could use to do that at your own instrument in your laboratory and check it out in quiet so that you have the way to do that 24 hours, 7 days a week. But let's start first with what is a wavelength dispersive X-ray instrument. And I have here a picture how such an instrument could look like. And I would like to explain you step by step how it works. So first of all, we need an X-ray tube which will excite our samples. That means the X-ray is coming out of the tube and is directly irradiating the sample surface. On that way, we could introduce a primary beam filter which will modify the X-rays in a way that only some elements are excited. And a good example for that is the tube normally has an anode material like rhodium. And if you would like to measure rhodium in your sample, then it makes sense that a primary beam filter takes away first the characteristic rhodium radiation, and so that the rhodium which is created in your sample can be seen then clearly by the detector. The second thing we have is a mask which limits the beam size in a way that it fits through the cassette of your sample so that the sample is only irradiated in the proper way. Then, of course, we have our sample and a collimator which takes away the fluorescence radiation created in the sample by the goniometer, which is the crystal and the detector. And this collimator are parallel plates which will lead for parallel X-rays directly going to the crystal. And the crystal has the job to reflect the radiation in a certain angle to the detector, which then finally registers our radiation as intensity. So the crystal always must be placed in a certain angle, and this depends also from the ladder distance inside the crystal material, so that the radiation, the wavelengths, is corresponding to the crystal and a certain angle, so that the detector takes in the end one single wavelength. Of course, the X-ray tube comes itself with a spectrum of X-rays, and this is characteristic for the tube. If it's, for example, a rhodium tube, you see here also the characteristic radiation. And then this radiation is going to the sample. And at the sample, X-ray fluorescence should be created. This is what we like to have. And this happens if from the inner shell, electrons are removed and electrons from higher shells are filling the gap. And if this happens in the K shell, we are talking about K lines. If it's in the L line, in the L shell, these are L lines and M lines. Yeah, so this is how the different X-ray fluorescence lines are created. Then these fluorescence lines are created by each element in our sample. And then we have this detection principle over a goniometer, which is watching the sample. And like I told you already, the goniometer is produced in a way that it just takes one single wavelength, so that in the end, when we look on the result, we get such kind of scan, which then shows the line. And the scan is created by moving the crystal, moving this angle around the middle of the theoretical line. And then this kind of scan is produced. What we see as intensity in the end is just this height of the peak either like it is here as a cross height, or if we also measure backgrounds, then it's only the net height where the background is subtracted before. What elements can we measure with X-ray fluorescence? In theory, it starts with beryllium and it goes down to uranium and of course the radioactive elements, but uranium is the element we see in natural samples. And but in real world, we normally start as oxygen or fluorine because the technical equipment we need to analyze also these light elements is very complex and expensive. So you need normally a crystal for every element of these special sort to identify them. So that in most XRF instruments, you start as oxygen or fluorine to detect the elements. Here I made you a list of the materials where you can make this kind of analysis. In the end, we are counting atoms of our elements. And so this means it's kind of an inorganic analysis. And that's why the materials like cement, steel, glass, or any kind of raw materials, minerals, plastics, mineral soils, fuels, fractories, or metals are the ideal samples because they contain the elements in either elemental or oxidic state. When we now create an application for wavelength dispersive XRF, we need first to create the measurement conditions to measure each element. In a second step, we have then to scan to adjust the lines for each element and also to set backgrounds. The third point is we have to define the energy limits for the detector. Next is we have to define how our report looks like. In the next step, we have to define the measurement times for each element and of course the corresponding background line. Then, because XRF is normally used over a long time, we should think about a drift correction program. That means we should introduce drift correction samples and create a corresponding measuring program. After this is all done, we should introduce calibration samples, mostly standard materials, and we have to measure them. In the next step, we would also discuss line overlap corrections to reduce the inter-element problems. Then we calibrate, which means we establish a relationship between our known concentrations and the intensities measured for every element. And then last but not least, we should validate our method, but this I will skip today. So now for each element, we need to establish for the X-ray tube a voltage and the current, how the sample is excited. In the next step, we have to select a collimator, which will decide about the resolution for this element and the intensity. So either we can select a high resolution with a lower intensity or inverse. Then also we need to select a crystal, which corresponds to the element we would like to measure. And then in the end, also the corresponding angle together with the detector, which is able to measure our element. So this results in a kind of a table where we have defined for an element like here copper, which line we would like to measure, for example, K alpha. Then we use a crystal, we use a corresponding collimator, a detector. In this case, we say no primary filter is used. The voltage and the milliamps for the tube are defined. And then the database gives us or proposes us an 2 theta angle for the detector crystal setting. But this is only a theoretical angle. So that means in the next step, we have to check this theoretical angle by a scan of our line, and then we need to correct it to the maximum. Why the maximum? Because we would like that if the peak shifts a little bit over the lifetime of the calibration, that we have the less change in intensity than possible. And this is, of course, in the maximum. And so this means for every element, we will do a scan, we will adjust the main line, and if necessary, we also would place a background line. This is especially important when we do trace analysis, so that we can correct for the background effect. And also, this is necessary when we want to measure net lines. And this means the background is used to create a horizontal line. And then at this point, the cross intensity is subtracted by the background intensity, which then leads to the net intensity. In some cases where we see our peak on a slope like here, then we would place two background lines, one on the left, one on the right, and then a background is constructed from the left to the right, and then the background under the line is calculated accordingly. For the backgrounds, we have to be careful that there are no other lines at this place, which will make a peak and then lead to problems during the evaluation. That means that we get wrong intensities because of a line overlap from a different element. In the next step, we have to talk about the detector. The detector is registering our line in a pattern like we see here. So it's so-called energy profile or pulse height distribution. And we have to define for the detector what channels are summarized to result in our intensity we get in the end. But most people are asking me, what is this? What does this picture mean really? And for this, I give you here the sketch of our spectrometer. So the detector is watching over the crystal our sample. And in this case, chrome Ka alpha line is reflected by the crystal into the detector. And in the end, it's a monochromatic line, so it's one wavelength only. But the detection process has an error, which makes the line broad. So this means the theoretical measurement would be only one line, but because the detector changes this result, we get a broad peak. And then additionally, in the case of chrome, we use a gas counter, a flow counter, which is filled with argon gas. And the argon is also excited by the chrome Ka alpha radiation. And the energy we lost, you see here as an escape peak. So the escape peak is also chromium Ka alpha radiation, but reduced by the argon energy. So that means in the end, to get the full intensity for chromium, we need to sum up from the left to the right side both peaks. And there are other cases where you would set the lower limit in the middle and you skip the escape peak. In the course we have on our platform, I will show you later on, there all these cases are described in detail and will help you to decide what case would be good for your application. When this is defined, then we have also to talk about the report, how it should look like. And then sometimes elements have to be recalculated as an oxide. You can also define what unit and what precision you want to have. Also, you can add other components you would enter like a manual input into the report, or you can do additional calculations. In the next step, we have to talk about measuring time. So how long do you need to measure to get a good result? And we have to talk about the measurement for the line and the background. And in the end, what we do in our routine measurement is that we set the goniometer to the main line. We measure, let me say, for a while. And after that, we set it to the background and then we measure again. So this results in a kind of a table like here shown, that for the line you have measurement times like 20 seconds, and for the background you have about 10 seconds. But how to decide how long you should measure? For this, I have added you a table here, and we should talk about the measurement error. Let's think about that this line measures with 1,000 counts per second, and you would measure it 1,000 seconds. So then the product of both would be 1 million counts in the total measuring time. If you take the square root out of this, then you have the measurement error. And based on this fact, you can decide now how long you should measure to get a certain count rate you would wish like for your measurement error you require for your application. And you just need to do a scan of your standard sample. You look at the intensity you get here, and then you can decide how long you have to measure to achieve a corresponding error. Let's talk about drift correction. In the end, we need to define drift monitors, and mostly not only one sample is necessary. You have to look for several samples which cover finally all the elements of your application. And then you have to establish a relationship between which element you measure in which sample. In the second step, you have then to create a measuring program and to measure each element. And then you have to be careful about the measuring time. It should be according to the rules I explained you already. It should be high enough so that the measuring error of the drift program becomes negligible, so that it will not destroy your analytical performance of your main calibration. After that, you have to decide if you need only a high monitor or a low and a high monitor. You should decide on a base if you measure backgrounds and your calibrations based on net intensities, like in this case, a high drift monitor is sufficient. And then you measure it just during the calibration, and later on it will be always compared what factor has to be established to correct all the different concentrations for the elements you're looking at. If you have no background measurements, then you should have two drift monitors, one at the low end, one at the high, and over the two measurements, the line is constructed, and then all the range of concentrations could be corrected. And of course, you should establish your drift monitor program during the calibration so that you have no time difference between calibration and making the drift monitor program. Then we come to the point where we have to enter the calibration samples into the software and the corresponding concentration for each element. And there normally you could also define the quality of the concentration. It is an informal value only, or is it a certified value? In the next step, you need to decide what is your calibration method look like. In an ideal case, for example, if you have traces in a polymer or in a liquid, you could just do a straight calibration line. You won't see any inter-elemental effects and you are done. But mostly in the XRF world, we are measuring solid samples and they all show curved calibrations. And in this way, we need corrections, inter-element corrections. And one possibility would be an empirical alpha corrections you introduce. But for an empirical alpha corrections, you need a set of standard samples, which is really representing all inter-elemental effects. And sometimes you need a very high number of standards for that. If this is not available, you should switch over to a theoretical alpha or fundamental parameter correction. This will then reduce the number of standards drastically. On the other hand, it also will need that you have to describe your sample 100%. So you have to measure all elements, or you have to describe any missing element over the software so that the software is able to calculate the sum to 100% for all your elements. Then you have to look to line overlaps. And of course, for any outliers in your calibration. I give you now two examples. The first one is an empirical alpha correction for these three samples. So we have here copper in 3 concentrations, and 2 of the samples do not contain chrome and the third does. This chromium concentration leads to this big deviation. And if we introduce an alpha correction, an empirical alpha correction, chromium on copper, then the software is able to correct for this effect, and then all 3 points fit on a line. So this is a typical example how to do that. Another example would be a line overlap correction. For example, here, the chromium Ca beta line is overlapped with the manganese Ca alpha line, so that the manganese intensity is a bit too high than it would be without chromium. So then we would introduce this line overlap correction, and in the calibration, our point will just come to the line like it should be. But now I would like to introduce you a new training concept, how all these kind of steps could be done at your spectrometer in your laboratory. And we use for this our FLUXANA platform. This is a training platform which was established beginning of this year, and we host there quite different kind of XRF training courses. And one of these is the new FLUXert calibration training you could use to calibrate your WD instrument. The course is available all day, all week, and it also is made for a calibration set we constructed especially for this purpose. This set is made by a 3D printer, so that means that it's quite cheap to produce it, and we could make it in high numbers. These are not standard materials or certified reference materials. These are only samples which contains elements with all these problems to train calibration for WDXRF. That's the purpose of this set. And the FLUXert calibration course is exactly corresponding with these samples. How is it built up? We have taken into consideration that there are different manufacturers of wavelength dispersive instruments in the market, and that's why also they all come with different software packages. You could also have a kind in the course, you have something like a feedback you could give us, and you even could give your own certificate. And there's also a forum introduced where you could ask questions to us and also to other users, so that you get also help when you get stuck in one of these different courses. And from the course, I just took out here one example, the measuring conditions, so that you see how different it is presented by the different software versions of the different manufacturers. And in this case, you will directly recognize your software and could adapt the course to what you need. And also the way it is presented inside the course, like you see here, this is following how it is really done in that special software. And you see at this example of the Type 2 course that we just start here with defining the measuring conditions, sample description, then we do the scan for every element, we define line and background position, adjust the detector, then we create a report and establish measuring times. Then we make here the drift correction program and link it to the analytical program. Then we define the calibration samples, we measure them, and then here you see the whole part of doing a calibration. And there we tried to explain how to do an empirical alpha correction, how to use the fundamental parameter program, how to establish a line overlap program, and how to handle outliers. So that step by step, you really can go through the whole calibration process. And in case you use this a FLUXert calibration set, then I just put here you the concentration levels, how it's spread over the different elements and the concentrations. It's very simple, but it's just made for this purpose. But it doesn't mean that you really need it for making the course. It is just a possibility. You could also take your samples and then just transfer these things to your elements you need for your application. Okay, I think that was my presentation to how to make a WDXRF calibration. So all the way through, all the points you have to take into consideration, and the possibility how we could help you to make this calibration on your own. And now I will have a look on the questions which were set up, which were come up in the question and answer section. Please let me have a quick look. So there is a question in the forum: while setting the element lines, you mentioned possible shifts. Can you describe what causes the energy shifts and ways to minimize this effect? So you have to see that over time, a spectrometer is aging. Things are getting older. So this means the high tension, for example, is a bit de-adjusted. So everything is a little bit under movement. And this is the reason why we have to set our energy profiles properly so that we collect the intensity in a good way. So even if the peak shifts a little bit to the left and the right, it will be recorded correctly and we still got the same intensity. And also the drift correction will help us to adjust this over time. And it's clear, as older an instrument, as more we will see these effects. So then I have here another question. Correction sample is the same than reference material. A correction sample could be, I think you mean drift correction. The drift correction would be an extra sample which is independent on the standard materials, because there we would like to see high intensities. And normally you use today class samples because they are very long time stable and you can clean them easily, and they could be also replaced in case. I have another question here. How often do we have to calibrate XRF for cements? I would establish a control sample in the cement application. You measure in a regular way. That means, for example, every week or every month. And as long as the control sample is in your limits, you don't need to do anything. When it's out, then you need to do a drift correction. If the drift correction is not able to correct for the effects, then of course you have to do a new calibration. There is another question: is your course available in other languages or with subtitles? In the moment not, I'm sorry, but we can think about this. This is a good idea. Another question: there is any possibility to use the set for energy dispersive XRF calibration? It would be, but there is no course for the moment. Yeah, so perhaps we could discuss this offline so that you send us an email and we can think about how we could help you to calibrate your energy dispersive XRF. So there is another question: how many hours do typically users need to complete the course? I would say you probably will need a full day, because the time to establish the measuring conditions, to scan all the elements, to check if everything is right, to redo the measurements, then to measure the samples, then to adjust the energy profiles for the detector. This all needs time. And if you really want to check this properly, you should take your time. And I'm sure you will redo it several times to get it really optimum. And this is the big advantage of this course. It's just there. You can enter all the time and you can always continue using it. There's another question: Do you sell the course per user, or do you consider a company license for multiple users? Generally, the course is really sold per person. However, we had companies who already bought a bunch of licenses, and of course, then they get a better price. So this is possible. Do you have any experience with 3D printing of iron and nickel metal alloy such that it can be classified as a CRM without measurement? This is, of course, a question a bit off topic, but indeed, we have a project in doing also 3D printing for metals. And but if they are really possible to use as a CRM, this is not yet clear because it depends a lot on the printing process, and there needs to be done more investigations. So let me see more questions. Do we really need a 0 point in a calibration curve? I think this is only necessary if you want to measure traces. That means if you are not measuring around 0, then it's not necessary. There's some other questions. How can we introduce high and low points of the drift correction samples in the calibration curve? That's a bit different in every software. So probably this we should discuss then over the forum in the course, or you send me an email. I think that we have to discuss extra because I have to know what software you're using, and then I can give you a better answer. I think all the other questions we will answer. We will collect this here. And at this point, I would like to thank you very much for joining our course. The number of people who have joined is really high, and that's really motivating us to do more of these events. And perhaps you have seen that there is already more webinars, like I announced here already for press pellet versus view speed. Have a look there. I thank you very much for joining us today. And yeah, see you in the forum then. Thank you very much. Bye-bye.